Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin, and we will continue with Chapter 8, Part 3, Reactions of Alcohols. So the first reaction we're going to talk about is the reaction of alcohols with active metals. Okay, reactive metals like lithium, sodium, and potassium can react with alcohols to generate hydrogen gas and form a metal alkoxide, or the metal salt of the alcohol. And we can use these for a number of different things. They are very strong bases. We can use them as nucleophiles, and we can use them as bases in beta elimination reactions. The reaction proceeds by taking a sodium in its elemental state, and it is oxidized to sodium +1. Those electrons have been transferred to the hydrogens, which form a diatomic molecule of hydrogen gas, and that leaves the solution. So the reaction goes and is irreversible. Okay, so for every 2 equivalents of alcohol you have, you will be able to generate 2 equivalents of your alkoxide, or in this case, because we are using methanol, our sodium methoxide. Okay, we can also take those alcohols and convert them to alkyl halides. We did that before. We converted alkyl halides to alcohols by using hydroxide. In the case of alcohols, we can now protonate that OH and then convert it back to alkyl halides. When we have water-soluble tertiary alcohols, this reacts very rapidly to form our alkyl halide and produce water. However, the lower molecular weight primary and secondary alcohols are unreactive to these conditions, and I will talk about that in a minute. Okay, so if we have water-insoluble tertiary alcohols, we can react these by bubbling gaseous HCl through the solution. That will still protonate the alcohol and make it a good leaving group and be able to convert our tertiary alcohol into our tertiary alkyl halide. If we use a primary or secondary alcohol, we have to use concentrated HBr or HI to convert them to the bromides or iodines, but reactions with the chloride, HCl, does not work without a catalyst. Okay. The mechanism for using a tertiary alcohol to convert it to a tertiary alkyl halide undergoes an SN1 mechanism. So basically, we're going to be able to form a carbocation with our tertiary alcohol. The first step in this is to transfer a proton from our acid to our alcohol to make it the oxonium ion, to make it a good leaving group. Once we transfer that proton to make it a good leaving group, we can then break the bond between the oxonium ion and the alkyl group, creating a tertiary carbocation and a neutral water species. Now that we have that tertiary carbocation, we can then have attack by a chloride or other halide as the nucleophile to generate our alkyl halide. Now, when we do this for primary and secondary alcohols, we don't go through an SN2 mechanism because we'd have to form a carbocation. We actually undergo an SN1 mechanism. But the first step is the same. We need to protonate the alcohol to make it a better leaving group. Remember, hydroxide is a bad leaving group. However, water is a good leaving group. So the first thing we're going to do is we're going to protonate the alcohol to generate our oxonium ion here. Now that we have a good leaving group, attacked by any nucleophile to displace that water will generate 2 neutral species, the alkyl halide and water. Sometimes, because we have to use such concentrated acids to generate those HBr, or those alkyl bromides and alkyl iodides, we cannot do that without a catalyst. So we use a different reagent to make it an even better leaving group. We use a compound called thionyl chloride, SOCl2. And so what it does is it generates an intermediate where the sulfur is binding itself to the oxygen to create a much better leaving group, and then we have attack by the chloride. So the key steps here are you have a water-insoluble alcohol, you have the reagent thionyl chloride, and then you add a catalyst. This is a basic catalyst called pyridine. It's an organic molecule that's a base. And during the conversion of this, you get your alkyl halide, your primary alkyl halide, or secondary alkyl halide, and then it generates SO2 gas and HCl gas. And again, this is in a non-aqueous environment, so those tend to bubble off, leaving us with a pure alkyl halide. Okay, so now that we've seen that we can convert alcohols to alkoxides, we can convert alcohols to alkyl halides, we can also take and dehydrate an alcohol by beta elimination. Now, we can't do this under basic conditions because we would have hydroxide as a leaving group or an oxide as a leaving group. So we actually do this with acidic conditions. So in the case of primary alcohols, we heat this with very high heat with an acid catalyst like sulfuric acid or phosphoric acid, and it typically takes some other catalyst to make this happen. It happens like 200 and 300 degrees C, but it will eliminate water and generate an alkene through beta elimination. The secondary alcohols undergo this dehydration a little bit easier at slightly lower temperatures, and tertiary alcohols require only slightly above room temperature and less strong acids. Okay, so an example of this would be if we take ethanol and heat it at 180 degrees with sulfuric acid, we'll generate ethylene gas and water. Okay, in the case of cyclohexanol, we now have a secondary alkyl halide. I'm sorry, a secondary alcohol, and that secondary alcohol takes less heat to generate the alkene. In this case, only 140 degrees Celsius with that same sulfuric acid catalyst. However, if we take a T-butyl alcohol, a tertiary alcohol, we only have to mildly heat it at 50 degrees in sulfuric acid to obtain an alkene derivative from it, which is our methylpropene or our isobutylene. So by increasing the degree of our alcohol, we keep decreasing the temperature required to have that dehydration beta elimination to give us our alkene. Okay. Now, when we do this, we want to make sure we follow Zaitsev's rule, meaning that the primary or the main isomer produced is going to be the more substituted double bond whenever possible. So in the case of 2-butanol here, we could form the double bond between the terminal methyl group or this internal methylene group. And what we see in the product distribution is we have 80% of it give us the di-substituted alkene, and only 20% of it gives it that mono-substituted alkene. So these acid-catalyzed dehydrations of alcohols to form alkenes follows Zaitsev's rule. The more substituted double bond is the major product. Okay, and the reason it does that is it follows a 3-step mechanism. In most of these cases, when you have an acid catalyzed, the first step is the transfer of a proton. And in the case of the alcohol, we do the same thing by adding the proton to the OH group, giving us the oxonium ion here, and also our neutral Lewis base water. Okay, the second thing that happens is we have water leave, generating our carbocation. And when we have our carbocation, we then have a transfer of a proton away. Remember, when the proton is taken away by our Lewis base, we have those electrons come in to form our double bond. And therefore, when we try to form that double bond in that more substituted area, we end up with the more internal alkene. Okay. In the case of a primary alcohol, we only have a 2-step mechanism. Because we can't form that primary carbocation, we have the first step is the transfer of proton to make the oxonium ion to make it a good leaving group. And then the remaining water in there acts as our Bronsted-Lowry base and forms a bond with the hydrogen, allowing the electrons to kick in and our oxonium to kick out. So technically, it isn't. It's an E2 reaction because we're using the water as a base, and it happens all in one step, giving us liberating one equivalent of water, regenerating our acid catalyst, and giving us our alkene. Remember, because we would have formed a primary carbocation, we cannot go through that 3-step process, we have to go through this 2-step process. Okay. So because we can do that acid catalyzed dehydration, we can also do an acid catalyzed hydration to generate the alcohol. Okay, and so we have to think about when we have this, the more water we have in that reaction, the more likely it is to be shifted to the alcohol side of the functionality. If you remove the water as the reaction progresses, it's going to go shift more toward the alkene side of the reaction. So these hydration reactions are in equilibrium. The dehydration and the rehydration are in equilibrium. So by removing water, you can drive it to the alkene. By adding water, you can drive it to the alcohol. Okay, we have 2 more reactions we can do with alcohols, and they both involve oxidation. So in the case of alcohols, we can convert that alcohol to different functional groups that have additional oxidation states. The first thing we can do is use what we call chromic oxide or chromic acid in solution, and we will either generate we will generate ketones, aldehydes, or carboxylic acids, okay? So if we have a primary alcohol, the first thing we're gonna do is we're gonna oxidize that to an aldehyde or a carboxylic acid, because a ketone has to have 2 carbons on it, and a primary alcohol is at the end of the chain and only has 1 carbon. So if we have a secondary alkyl, a secondary alcohol, we can convert that to a ketone. So let's look at how that works here. In the case of this primary alcohol, 1-octanol here, what it's going to do is, the first thing it's going to do is remove 2 hydrogens, 1 from the alcohol and 1 from the carbon, to generate this intermediate aldehyde compound right here. Chromic acid is a very strong oxidizer, so it's very difficult to stop at this state, and it actually oxidizes again, transfers an OH where the hydrogen was, and creates our carboxylic acid. So chromic acid by itself will always convert primary alcohols to the carboxylic acid. If we want to stop at that aldehyde, we have to use a slightly less reactive reagent. And to stop at that aldehyde, we have to use a compound called PCC, or pyridinium chlorochromic. By converting the chromic acid with HCl and a base pyridine, we create a complex that's less oxidative than the chromic acid was. And because it is less oxidative, or not as strong an oxidizer, we can stop it at that aldehyde step without going all the way to the carboxylic acid. So when we think about this, we think of, number 1, it's a primary alcohol we're reacting this with. We're going to use PCC in some solvent that doesn't oxidize, okay? So in the case of that, when a solvent doesn't oxidize, we can stop it at this aldehyde functionality. So if we want to convert to a carboxylic acid, our primary alcohol to a carboxylic acid, we use chromic acid. If we want to convert our carboxylic acid, our primary alcohol to an aldehyde, we use PCC. If we want to convert our secondary alcohol to a ketone, we can use either reagent. And because tertiary alcohols don't have a hydrogen on the carbon, they don't oxidize with either of these reagents. They're very difficult to oxidize. And in fact, we would typically convert those to our alkenes or alkynes. And that is our reactions for alcohols.